Hello everyone, my name is Jeff Tang and this presentation is for my final project in CSCI 222 Foundations of Large Language Models. The title of my project is RAG for Open Domain Question Answering over a Custom Corpus. In this project, I designed and implemented a full retrieval augmented generation pipeline or RAG pipeline over a YOP review corpus using modern LLM tooling including FAST, mini-LM embeddings, a cross-encoder rerunner, and a Google Flan T5 Large. The goal of the project was to build a system capable of answering natural language questions over a large collection of unstructured reviews while reducing hallucination and improving factual grounding. The dataset is the YOP review polarity dataset, containing approximately 560,000 training reviews and 38,000 test reviews. Due to hardware constraints on my MacBook Pro M3 system, I used a subset of 50,000 reviews for indexing. For retrieval, I used the mini-LM L6v2 embedding model together with a fast index flat IP vector index. For generation, I selected the Google Flan T5 Large, which is an instruction-tuned encoder-decoder model based on the T5 architecture. The project also includes evaluation using hit-at-k retrieval metrics and several qualitative analysis and visualizations. One important design goal was to build a practical, reproducible RAG system that could run locally without requiring expensive GPU infrastructure. The core problem addressed by this project is that traditional keyword-based search performs poorly on complex natural language questions. For example, users may ask questions like, "What complaints appear most often?" or "Do people generally describe the service positively?" Traditional search engines rely heavily on keyword matching and cannot effectively synthesize information across multiple documents. Large language models can generate fluid answers, but they often hallucinate or lack domain-specific knowledge. At the same time, organizations already possess massive repositories of unstructured text data, such as reviews, logs, customer feedbacks, and support tickets. But extracting insights from this data usually requires significant manual effort. Retrieval augmented generation addresses these problems by combining semantic retrieval with grounded generation. Instead of relying only on the model's internal memory, the system first retrieves relevant documents and then conditions the generator on those retrieved chunks. This improves transparency, grounding, and factual consistency without requiring expensive model retraining. The motivation for this project comes from real-world industry use cases. Many enterprises already have large internal knowledge repositories, but non-technical users cannot easily query them using natural language. RAG systems help bridge this gap by allowing users to ask questions conversationally. Another important motivation is reducing hallucination risk. By grounding answers in retrieved evidence, users can better understand where the generated answers come from. Some example questions in the system can answer include, "What do reviewers like most?" "Is service usually slow or fast?" "Which complaints appear most frequently?" And "Is this restaurant family friendly?" The overall goal was not just to generate text, but to produce answers that are grounded in actual retrieved reviews. This slide shows both the dataset scale and the overall RAG pipeline. The project uses 50,000 YOP reviews, which after chunking produced over 84,000 indexed chunks. Reviews were split into overlapping windows of 120 words with 40-word overlap. Overlapping chunks help preserve context across chunk boundaries and improve retrieval quality. The pipeline itself consists of several stages. First, the corpus is loaded and cleaned, and then the reviews are chunked and embedded using mini-LM embeddings. These embeddings are indexed in FAST using cosine similarity search. At query time, the system retrieves the top candidate chunks, applies sentiment filtering and re-ranking, and finally sends the retrieved evidence into FLAM T5 large for answer generation. This architecture follows the standard retrieve then generate pattern commonly used in modern production rack systems. The next slide explains the three major model components. First is the embedding model, all mini LM L6V2. This model generates 384 dimensional semantic embeddings and is optimized for semantic similarity tasks. Second one is the re-ranker, cross-encoder MS Micro Mini-LAM L6V2. Unlike bi-encoders, cross-encoders jointly encode the query and document pair, allowing more precise relevancy scoring. Third is the generator, Google FLAM T5 large. I selected this model because it provides a strong balance between instruction following capability and hardware efficiency. One important engineering constraint was that the entire system had to run locally on an Apple M3 Pro MacBook without CUDA GPU support. The embedding stage used Apple MPS acceleration, while the re-ranker and annihilator ran on CPU. The next slide shows the retrieval pipeline in more detail. The retrieval system uses 5 stages. First, the query intent detector classifies the query as positive, negative, or neutral using lightweight rule-based keyword matching. Second, FAST retrieves the top 15 semantically similar chunks. Third, the sentiment-aware filtering removes chunks whose sentiment does not match the query intent. For example, a complaint query should primarily retrieve negative reviews. Fourth, the cross-encoder re-ranker refines the ranking using a hybrid score that combines re-ranker logics with FAST similarity. Finally, deduplication and diversity enforcement prevent repetitive chunks and ensure balanced retrieval for neutral queries. These additional pipeline stages significantly improved retrieval precision compared to naive dense retrieval alone. The prompting strategy in this project is intentionally simple. The focus of the project is retrieval quality rather than advanced prompting engineering. Retrieved review chunks are inserted into a structured prompt template together with the user question. The generator is instructed to summarize the major patterns across reviews, including both positive and negative aspects if applicable. I used greedy decoding with repetition penalties and no repeat n-gram constraints to reduce repetitive outputs. One important trade-off observed during experimentation was that stronger grounding instructions reduced hallucination but also increased extractive behavior, where the model copied chunks directly instead of abstracting them. This slide shows several example outputs from the system. For praise-oriented queries, the system retrieves positive reviews and synthesizes common positive themes. For complaint-related queries, the system correctly identifies service-related complaints as dominant issues. The generated answers are generally coherent and grounded in retrieved evidence. One limitation is that smaller generations like FLAM T5 large sometimes concatenate retrieved chunks rather than producing fully abstractive summaries. However, the system still demonstrates meaningful semantic synthesis across multiple reviews. The next example demonstrates one of the more interesting capabilities of the system, The query is, how do people describe the service? Since this query is neutral rather than explicitly positive or negative, the diversification step intentionally retrieves both positive and negative chunks. The retrieved documents include examples of poor service experiences as well as extremely positive customer service interactions. This balanced retrieval produces a more nuanced and realistic answer. It also demonstrates why diversification and re-ranking are important components in RAG systems. Quantitative evaluation used the hit at k retrieval metric. Hit at k measures whether at least one retrieved document contains an expected keyword relevant to the question. The system achieved an average hit at 3 score of approximately 0.67 on the evaluation questions. One important observation is that keyword-based metrics underestimate semantic retrieval quality. For example, retrieved chunks may contain semantically equivalent language without matching the exact expected keywords. This visualization projects chunk embeddings into 2 dimensions using PCA. Positive and negative reviews show partial clustering, but still exhibit substantial overlap. This is expected because mini-RM embeddings capture semantic meaning rather than sentiment labels. The visualization supports one of the key findings of the project. Embedding retrieval alone is insufficient for sentiment-sensitive queries. Additional re-ranking and filtering layers are necessary. This chart shows the similarity scores for the top retrieved documents for a complaint-oriented query. The scores are tightly clustered with only a small spread between the highest and lowest ranked documents. This means fast retrieval alone has weak discriminative power. Many documents are semantically similar but not equally relevant. This visualization helps justify the addition of the cross-encoder re-ranker, which provides much stronger fine-grained relevance scoring. This slide demonstrates the impact of filtering and re-ranking. Before re-ranking, the raw fast retrieval contained many sentiment misaligned documents. For a praise query, negative reviews still dominate the candidate list as an example. After filtering and re-ranking, the final retrieved documents were fully aligned with the positive query intent. The cross-encoder successfully prompted more relevant documents higher in the ranking. This was one of the most important findings of the project. Dense retrieval alone is not sufficient for high-quality grounded question answering. This system has several strengths as we talk about the strengths and of the limitations. The two-stage retrieval architecture improved precision significantly. Intent-aware filtering reduced sentiment mismatch. The pipeline is modular, efficient, and fully reproducible on consumer hardware. At the same time, there are important limitations. The embedding model is not sentiment-aware. The generator sometimes copies retrieved text rather than fully abstracting it. The evaluation dataset is relatively small, and the YOP dataset itself is not designed specifically for question answering tasks. Despite these limitations, the project successfully demonstrated the core engineering patterns used in modern RAG systems. There are several possible filter extensions. Larger instruction-tuned generators such as Llama 3 or Mistral could improve answer quality. More advanced evaluation frameworks like RAG-AS could provide better metrics for faithfulness on the answer relevance. Approximate fast indexes such as HNSW could improve scalability to millions of vectors. Fine-tuning the embedding model on domain-specific QA pairs could also improve retrieval precision. Finally, the system could be extended into a conversational RAG assistant supporting multi-turn interactions. In summary, this project implemented a full end-to-end RAG pipeline over a large Yelp review corpus. The project demonstrated that semantic retrieval alone produces many moderately relevant candidates, while re-ranking, intent filtering, and diversification are essential for generating grounded, high-quality answers. The final system successfully integrates mini-LM embeddings, fast retrieval, cross-encoder re-ranking, and FLAN-T5 large generation into a practical and reproducible architecture. Overall, the project demonstrates many of the same architectural pipelines used in real-world enterprise RAG systems today. And that is the end of my presentation. Thank you for watching. The video is available in the link below. Thank you.